So this one says transition metal complexes often have different shapes and may form a number of stereoisomers. It says, describe the different shapes and the different types of stereoisomerism found in transition metal chemistry, and use suitable examples and diagrams in your answer. So as with any levelled response question, it's always worth doing a quick plan to put your information and what you already know down. So a bit of recall is required here, just to try and compartmentalise all the different shapes and stereoisomerisms into what fits in with what. So this now gives you a guide to follow, and don't forget to use suitable diagrams and examples in your answer. So first of all, looking at a typical octahedral complex, we'll deal with cis and trans first of all. If we take the identical ligands here, in this case to be NH3, you can see that they're 90 degrees apart in the top version and 180 degrees apart in the bottom version. So you have 6 ligands and 90-degree bond angles throughout with octahedral complexes. Not forgetting, of course, our square brackets and our charges. So, checking our plan, we've done cis-trans isomerism in octahedral complexes. We've now done cisplatin and transplatin as an example of cis and trans in square planar. So the bond angles are 90 degrees throughout in this case, and 4 ligands again. So doing a quick check of our plan, we still have to do the things that are underlined with an asterisk next to them. So we haven't dealt with tetrahedral yet, and we haven't dealt with the optical isomerism found in octahedral complexes when bidentate ligands are present. So what we need to do now is to bring the page down a bit to address these. So I've got rid of my plan. You could obviously cross yours through and bring the page down a little bit. So in this space that we've got, I can stick something down about tetrahedral complexes as well. So it's worth at this point thinking about not just the bond angles, but also the number of coordinate bonds. So I'm going to move the page down in order to make some room just to clarify this. So for octahedral I've got 6 coordinate bonds, for square planar I've got 4 coordinate bonds, and for tetrahedral I have 4 coordinate bonds. So the final thing I've got to do is deal with optical isomerism in octahedral complex. So to do this I need to make a little bit more room on the screen. So this phenomenon occurs when octahedral complexes contain bidentate ligands. So for example, if you had copper triethylene diamine, in other words, 1 copper and 3 ethylene diamine ligands, each ethylene diamine ligand is bidentate because there's a lone pair on each of the nitrogens. So this means that it can form 2 coordinate bonds. We've got a total of 6 possible coordinate bonds, so these can wrap themselves around partially the central metal ion. So you could draw one version like that, for example, and the other version like that. So if you look carefully, although they look similar, they're actually non-superimposable mirror images. So it's worth pointing out at this stage. So there's lots of other examples you could use, provided you explain clearly what you're talking about and you use appropriate examples and correctly drawn diagrams. Okay, so that takes us to the end of this rather applied transition metals question. I think it was the last question on the particular paper we're talking about. It was, not easy, and considering you were doing a 2¼ hour paper, this is probably the time when you're going to start getting a bit short for time. So hopefully this has been a helpful outline of how you might approach this type of question, both parts of it, the calculation part and the level response part. So until next time, thanks a lot for listening and see you soon.